The last thing that I want to recapitulate from your basic finite element course is the idea of the isoparametric element formulation, which where you remember we map a physical element, let's say a four-noded quadrilateral, from a parent element, which in case of the four-noded quadrilateral is a four-noded square. The parent domain will denote it by the square symbol, and it is spanned by, the parent domain is spanned by a set of vectors that we will denote as zeta. So in this case, this will be zeta 1, this will be zeta 2, and the physical element is in some coordinate system x1, x2, such that, or x1, x2, x3 if it's 3D, such that any point in the physical element denoted by x1, x2 is mapped from a corresponding point in the parent element. This point is, let's say, zeta 1, zeta 2, by means of a function which is this. So x, which is x1, x2, x3 in the 3D case, can be obtained from the values of zeta 1, zeta 2, zeta 3 in the parent space. And any point in the physical element is as usual interpolated from the values at the nodes using these shape functions ni. So as usual we write xi equal to ni xii, where, as you remember, ii has to occur together. Capital I denotes the node number and small I denotes the direction. So ni are shape functions which are now functions of zeta, and in the isoparametric formulation the displacements are also interpolated in the same way as the position. So therefore ui, the displacement in the ith direction at a point in the parent zeta at a time t, is interpolated from the nodal values at time t times the shape function. So so the displacements at this point would be interpolated from the displacement, let's say u1 at this point would be interpolated from the displacements u1 e, u3e, sorry, u1 2, this would be u1 1, u1 2, u1 3, and u1 4, where this is node number 1, node number 2, node number 3, and node number 4. Similarly, u2 at this point will be interpolated from u21, u22, u23, and u24. So, and the interpolation would be n1 u1 1 plus n2 u1 2 plus n3 u1 3, and so on. Now this again allows us to do the gradients and other things in the usual tensorial manner. So if I want, let's say, del ui del x j, so the gradients of the displacement, then I do del xj of ni uii. uii's are not functions of x, therefore I have to do ni del xj uii. Now we know that del ni del xj, ni is a function of zeta, so ni's are defined in the parent coordinates, and therefore to do del ni del xj we need to do chain rule. So to do del ni del xj, sorry, del ni del xj, we have to do del ni del zeta k del zeta k del xj. So this is the chain rule because these derivatives are known. Ni's are functions of zeta, So we use the chain rule to find the derivatives of ni with respect to x. And this matrix here is denoted by the inverse of the Jacobian, and we'll also denote it sometimes by gamma. So this inverse of the Jacobian connects the derivatives of the shape functions with respect to x to the derivatives of the shape function with respect to zeta. So um, when we do this, again we use uh, we use this here. So this will become del ni del xj u I and j kj inverse. So del ui del xj will be related to the derivatives of the shape function through this relation here. Now you might already have been told how to calculate this inverse of the Jacobian, but we will go through it. We'll take an example, simple example of a four-noded quadrilateral and go through the process just so that you recollect how this exactly is done. Uh, so here is the problem. This is a four-noded quadrilateral. These are the node numbers. So this is your parent, node number 1, 2, 3, and 4. These are mapped to these nodes 1, 2, 3, and 4 in your physical element. And this parent lies in the zeta 1, zeta 2 space and has uh, length and breadth of 2. So it's a square, 2 by 2 square, which is then stretched and pulled and mapped into this physical element. The isoparametric mapping is done in such a way that it is one-to-one. What it means is that this edge, which in the parent is, let's say, zeta 2 equal to 1, will be mapped to this edge. So this edge in the physical element corresponds to zeta 2 equal to 1. This edge corresponds to zeta 2 equal to minus 1. Similarly, this edge corresponds to zeta 1 equal to 0. So this is zeta 1 equal to 0. Similarly, this is zeta 1 equal to plus half. This is zeta 1 equal to minus half. Zeta 1 equal to plus half is the map of this line on to zeta onto this line in the physical space. Minus half is this line mapped from here. Similarly for zeta 2. So this is zeta 2 equal to half, zeta 2 equal to minus half mapped from this line, and zeta 2 equal to plus half is this line which maps to this. This is zeta 2 equal to 0. So every line, every point in this parent space is mapped to one and only one point in the physical space. And now once this is done, we can now write the derivatives using a chain rule. This is two dimensions. So as I said, del zeta 1 of something is equal to del x1 times del x1 del zeta 1 and plus del x2 of that something times del x2 del zeta 1. Similarly, for del zeta 2, I have del x1 del x1 del zeta 2, del x2 del zeta 2. Remember that this mapping is denoted by x equal to a function of zeta. So this is your mapping function for the isoparametric. This is known for a particular element. We know how these lines are mapped onto these lines. It's done through this equation. So once you know this, then it is easy to calculate del xi del zeta j, for example. So these can be easily calculated, and therefore these quantities here are known, and these constitute the Jacobian. So I can write this chain rule, the chain rules, to connect the del zeta 1 and del zeta 2 of a quantity, gradients in the gradients in the parent space, to gradients in the physical space through this matrix, which is called the Jacobian. And for reasons that will become clearer, we will denote this Jacobian by J zeta, and this zeta indicates that it's a Jacobian for the isoparametric formulation. We will encounter a different kind of Jacobian later. So to distinguish it from that, we will denote it by this J zeta, which is the isoparametric Jacobian that maps from the parent to the physical space. So this Jacobian connects the derivatives in the parent space to the derivatives in the physical space. And of course, we have the isoparametric map given by x zeta in terms of the shape functions. These are zeta 1, zeta 2, I'm sorry. I'll correct it when I upload. So this is the equation xi equal to n capital I x II. This is equation written for I equal to 1 and 2 in these two equations. So once we have this, we can calculate this quantity. So xi is this. So del xi zeta j is derivative of ni with respect to zeta j times xii. So this is, so del x1 del zeta 1 will be del n1 del zeta 1 x1i. So this is how we are going to write it. So this is how the Jacobian would be written, and this can be completely specified if we know the coordinates of the nodes of the parental of the physical element and the shape functions. So for a four-noded quadrilateral, these are going to be the shape functions. And you know the shape functions satisfy the Kronecker delta property. So these functions satisfy the Kronecker delta property. So if you know these shape functions, you can calculate each of these derivatives. Remember, these derivatives are with respect to zeta. So you can calculate these derivatives, and of course you know the nodal coordinates. So this can now be inverted. This matrix can be inverted. If it's a one-to-one mapping as we envisage it to be, so this mapping is one-to-one, so that every point in the parent maps to one and only one point in the physical element. So if this mapping is one-to-one, then the inverse of j zeta exists, and it is j zeta inverse. We sometimes call it omega. So omega is the function, omega is the matrix that now connects the derivatives in the physical element to the derivatives in the parent space. Just like J connected the derivatives in the parent space to the physical space, J inverse connects the physical space, derivatives in the physical space to the derivatives in the parent space. And these shape functions would differ for different kinds of parents. For a four-noded, it is this. For others, it will be a different set of functions. But whatever they are, we can always calculate their derivatives with respect to zeta 1, zeta 2, and if it's 3D, zeta 3 as well. Now, once we have done this, the formulation is complete, and we can get any quantity based on whatever we have learned so far. So, for example, if I want epsilon ij, and I have already seen it is equal to bij ik uik. This is what the strain is, and this is defined as del ni del x small I delta kj. Del ni del small I will be uh, you will get it from here, replace this by omega, then it will be omega im del ni del zeta m. So this will be del ni del small xi times del kj. So this will allow you to write the strain epsilon ij in terms of the derivatives with respect to zeta, which we can calculate from these equations. So this is how the formulation goes, and once you have everything mapped into functions of zeta, then the integrations that you have to do in order to find the stiffness matrix and so on can be done in the zeta 1, zeta 2, zeta 3 domain. The advantage of doing that, as you probably already know, is that the parent domain is a fixed domain, and therefore we can always do the integration over a fixed set of limits. Integration limits, in this case -1 to 1 for zeta 1, zeta 2 and zeta 3. So there are some restrictions on the Jacobian map. We need the Jacobian determinant of the Jacobian always to be positive, so that the mapping is 1 to 1, and we also need that x zeta is at least C0 in space. The reasons for that might have been already discussed in your finite element courses. So these conditions will ensure that it is 1 to 1 and invertible. So this is invertible, which means that a inverse of j zeta does exist, and if it does not exist, then we cannot do these operations, because these depend on the inverse, so we won't be able to do these operations properly. So it is essential for this formulation that that this omega exists. Sorry, this is not omega, this is gamma. So this gamma exists, and j is invertible. So a one-to-one mapping is necessary for this, but then all the advantage is that all integrations are now performed over the parent domain. So now f internal is, we have already seen this, it is del ni del xj sigma ji, and now this can be converted, this limit which is over the physical space can now be converted to the parent space, provided I replace this by j zeta d square, which is the element, a small element in the parent space, and j zeta is the determinant of the bold j zeta, and this affects the coordinate transformation that converts this physical domain into the parent domain. The integration converting to the parent domain allows us to use Gauss quadrature of a requisite order. The order depends on the polynomial hidden in this expression, but once we know the order, we do not calculate this integral explicitly. We do it through Gauss quadrature by converting it into a summation from I equal to 1 to n order, and depending on the order we have weights and integration points zeta I. This domain for rectangular elements and cubical elements is always -1 to 1 for zeta 1, zeta 2, zeta 3, and therefore these weights here and these sampling points are always fixed. They are predetermined from the Gauss quadrature tables that we have access to, and based on that we can do this integration as a summation over Gauss points weighted by these weights. And also remember that this is also a function of zeta. The Jacobian is in general a function of zeta. So when you take when you take values at sampling points, you have to take the values of this, as well as the values of this over the sampling points. So this completes our study of the isoparametric formulation. We will be using the isoparametric formulation, and particularly we will be interested in rectangular elements most of the time. So we will be mapping them from squares or cubes in the parent space, and we will be performing integrations, Gauss integrations over domains that range from -1 to 1 in all the three parent variables, parent coordinates. Uh, the isoparametric formulation for triangles is also well established, and you can find it in basic textbooks on textbooks on finite element. I'm not going into that, but all that I have told, except this last step where the Gauss quadrature weights and the sampling points would be different for triangular elements. Uh, Apart from this point, everything else that I have done carries over nicely to triangles, but we will not discuss it any further, and we will go over in the next week. We will start with the sources of geometric nonlinearity in problems in solid mechanics. So we'll start with recapitulation of continuum mechanics, which many of you may or may not have done. Um, so for the benefit of everybody, we will go through continuum mechanics very quickly, and try to figure out where the sources of geometric nonlinearity lie in a problem where the strains are not necessarily small.